Welcome back. Today, probability concepts, some basics. First, what's probability? It depends on who you ask. How often something tends to occur would be the answer that a frequentist would give. Frequentism is kind of a limited set of Bayesian approach. The Bayesian would say, well, probability is the measure of the strength of your belief. So this belief can be built on the number of times something has happened before, but it doesn't necessarily have to be. The most basic formula we have for probability is the number of outcomes x over the number of all possible outcomes. Usually the numerator is called the number of desired outcomes, but I don't think that applies in plenty of cases. So I just say number of outcomes x over number of all possible outcomes. So this yields us a proportion then, because we divide the numerator by the denominator. In this case we have a proportion of 3 over 5 equals 0.6. So if this is the chances that my dentist would recommend this toothpaste, the burning question, well, 3 out of 5 dentists surveyed said that they would recommend this toothpaste. So I might guess that there's a 60% chance that my specific dentist would recommend this toothpaste. But what I did there was I translated this proportion, which proportion runs from 0 to 1, to a percentage, which runs from 0 to 100, although you could have over 100 in specific contexts, just not in probability contexts. To get the percentage of a proportion, you just multiply it by 100. So let's use our new tool. Let's use our new tool like a Bayesian to figure out how confident we should be in something. We're thinking about a draw. X could be the number of tickets that you purchased. Your chance of winning the draw would be X divided by the total number of tickets that were sold, including the ones that you bought. So if we're at a minor league hockey game and they have a fundraiser, a 50-50 draw, and we know that they sold 433 tickets, maybe because they printed 500 and they have 67 left in their hands, and you bought 5 of them, your chances of winning, or your confidence that you should have in winning, would be 5 divided by 433. This yields a proportion of 0.0115, or a percentage of 1.15%. So your chance of winning is just the proportion of tickets sold that you purchased. You should be about 1% confident that you are going to win. What this means pragmatically from a Bayesian standpoint, where we're talking about confidence, is that if someone comes up and wants to make a bet with you that you're going to lose the 50-50 draw, so they're making a bet against you, you then would be betting on your winning the 50-50 draw. The only fair or even bet would be if this person gave you 99 to 1 odds against. In other words, if he said he would give you $99 if you win, but you would have to give him $1 if you lose. If we take that and we run that scenario 100 times, we would expect, because you have a 1% chance of winning, that you would lose 99 times and you would win once. So you would have gained the $99 from winning once, and you would have lost $1 99 times. In other words, you would have broken even. Let's put this simplest probability formula to work a little bit more. Let's say you roll 2 fair, normal, 6-sided dice. What is the probability of their sum being 3? What we have here are 2 images, and they both depict all of the possible results of rolling 2 dice. So we have 6 times 6 equals 36 possible results of rolling 2 dice. Both the tables contain the same information, just displayed a little differently. So, looking at these tables, there's 2 conditions in which a 3 is rolled, and all of the other conditions are different numbers. So the probability of your roll summing to 3 is 2 divided by 36, or 1 divided by 18 if you're a fraction reducer, which is 0.055555 repeating, or about 5.6%. These visualizations of all the possible combinations that could come up with the roll are a great introduction to sample space. The sample space is the space containing all the possible outcomes or results of an experiment or an event. If you throw 2 dice, the result will be one of these combinations. Or at least, if there is a result, it will be one of these combinations. This table is exhaustive. It contains all possible results. Another place where the sample space concept is used is when sampling from a population. Let's say each of these dice represents a person, or each of these combinations of dice, all 36 instances, represents a person. If I'm trying to estimate how my population of 36 people feel on average about whether we should teach critical thinking in grade school, 2 being strongly disagree, 7 being neutral, and 12 being strongly agree, I may, since I can't ask everyone, sample from that population at random. Let's say I randomly select these 5 individuals to poll and I get their results. The average is 4 plus 6 plus 7 plus 6 again plus 10 divided by 5. So that's 33 divided by 5, 6.6. In other words, the population seems neutral about it, which is probably pretty accurate, as we can see that the actual average of the entire population would be 7. Here, what is called sample space is all of the possible combinations of people, or all of the possible samples that could have been obtained. In this context, we can ask of a study or a survey who or what was in its sample space, and we can be critical of attempts to predict outside of it. If, for example, we wanted to draw conclusions about our population of 36 people, but we only had access to possibly sample 2/3 of them, then the results of those 2/3 might not be representative of the population on average. In this case, the average would be low, and especially not representative of the excluded third. So in this case, the excluded third has a very high average, 5s and the 6s combination. And the 2/3 that constituted our actual sample space, is estimating low. The constrained sample space is unfortunate for our estimate of the average, but it's even worse if we attempt to apply our findings to this excluded third, because our numbers are even more off for them. This brings us to the first rule of probability. What you have needs to sum to 1. You have a probability of x and a probability of not x, and if you get both of those numbers and add them together, they should sum to 1. If they don't, something's wrong. This is one way to catch errors in your thinking, is to ask yourself probability questions in 2 ways. What do you think your chances of success are? Then you ask yourself, what do you think your chances of failing are? If these numbers don't sum to 1, then there's something in your thinking that might benefit from being addressed. Maybe you're overestimating success, maybe you are overestimating failure. The beauty of this evaluation is that you know something is off, and it is not a matter of differences in opinion. You, on the whole, are contradicting yourself. But let's get back to sample space with an example that isn't dice and is not survey sampling. In probability, the idea of a sample space is very useful for getting one's head around any given problem. This is a question that is by no means intuitive to answer, but go ahead and give it a shot. There is a 75% chance of rain tomorrow and a 75% chance of rain the next day. What is the probability that it will rain in the next 2 days? I gave this question to the students in my graduate class in Statistics for Forensic Science. So all of them had science undergraduate degrees, and all of them were in a graduate level statistics class. And yet, I got 4 different answers from the class to this question. It's not easy. I invite you to pause and try to work out an answer for yourself, to experience the torture that is figuring this out and then not knowing whether you're necessarily 100% correct. Now, of course, there is a formula to help us, and this is called the second law of probability, or the sum rule, at least the sum rule for overlapping variables. But, of course, life doesn't come with instructions for when to apply this particular formula versus the many others that you may recall from high school or university. Here is how you would compute it, but that's not very gratifying because this wouldn't necessarily help me know when to apply this formula in the future. One way we can get the answer without knowing which formula is the correct one, and without reinventing the formula with our genius, would be to map out the entire sample space and then add up the favorable X or rain events. So what do we have? Let's check it the grunt way. Tomorrow, it can only rain or not rain. The day after that, it can only rain or not rain. So we have a probability of it raining on both days. That's 0.5625. The probability of it raining and then not raining. The probability of it raining and then not raining, which is 0.1875. The probability of it not raining and then raining, which is also 0.1875. And the probability of it not raining and then not raining, which is 0.0625. The last bit of the sample space is the only bit where it did not rain over those 2 days. So the rest of the probabilities could be added up to give the probability of it raining in the next 2 days, or you could just subtract the not raining value, 0.0625, from 1. Note that the proportions or the probabilities in sample spaces always have to sum to 1. It's very easy to make a mistake where you forget to multiply two proportions together. So if you map out all the possibilities and the total probability is not 1, you've either hacked the universe or you have made an error. And what are these different branches in your sample space? These are different realities, and the realities don't lie. Before we move on, let's learn something important. Memorize this sentence. Conditional probabilities are not symmetrical. You don't have to know what it means yet. Just try to get the rule into your head. Conditional probabilities are not symmetrical. First, some examples that are 100% obvious. The probability that you are Canadian, given that you have been Prime Minister of Canada, is near certain. Note that we're good scientists, and we try not to ever be certain about our estimates. But of course, the probability that you will have been Prime Minister of Canada, given that you are Canadian, is supremely unlikely. Okay, conditional probabilities are not symmetrical. So far, nobody will be arguing against this. So let's move on to a similarly obvious, but not quite as obvious example. I happen to be 6 feet tall. If I see someone taller than myself, the chances are very good that this person is a male. In other words, the probability that the person is a male, given that they are 6 feet tall or taller, is very high. But this does not mean that most males are over 6 feet tall. The probability that someone will be over 6 feet tall, given that they are male, is actually pretty low. Let's get more specific with this example, starting with the second conditional. Since we have Canadian norms, we can compute how likely one is to find a male who is 6 foot or taller, given one has found a male. Males in Canada average 5 foot 10 inches with a standard deviation of 3 inches. So being 6 feet tall would make a male 6 foot minus 5 foot 10 inches, 2 inches different from average divided by 3. That would make a male who is 6 foot tall have a Z-score of 0.67. And we can convert that to a percentile of 75. In other words, anyone 6 feet and taller is taller than 75% of Canadian males. So the specific probability of being over 6 feet tall, given that you are a male, is 25%, or low. Pertaining to the first statement, that your probability of being a male, given you are over 6 feet tall, is high, we would now need, for comparison, the proportion of females who are 6 feet or taller. Females in Canada average 5 foot 4 inches tall, with a standard deviation that at least rounds up to 3 inches. So being 6 feet tall would make a female 8/3, 2 2/3 standard deviations above average. This z-score of 2.67 would convert to a percentile of 0.996. In other words, anyone who is 6 feet tall or taller is taller than 99.6% of Canadian females. But we still haven't figured out the value for the probability in red. What is the probability of someone being male given that they are 6 feet or taller? Let's lay out our entire sample space. Assume half of Canadians are female and half are male. 99.6% of that 50% of Canadians is under 6 foot tall, so 49.8% of our population is female and under 6 feet tall. 0.4% of that 50% of all Canadians is over 6 foot tall, so 0.2% of our population is female and over 6 feet tall. Moving on to males, 75% of the half of all Canadians that is male is under 6 feet tall, so 37.5% of our population is male and under 6 feet tall. And 25% of the half of all Canadians that is male is over 6 feet tall, so 12.5% of our population is male and over 6 feet tall. Finally, we just use the definition of probability from earlier. Probability equals the number of outcomes x divided by the total number of outcomes. The total 6 foot or taller outcomes is 0.2 from the females plus 12.5 from the males, equaling 12.7. Dividing the males by this total yields 98.4%. So, the probability of the person being male, given that they are 6 feet or taller, is 12.5 divided by 12.7, 98.4%. So, the chance of being 6 foot taller, given you're male in Canada, is 25%, while the chance of being male, given that you are 6 foot or taller in Canada, is 98.4%. This shows us again the usefulness of laying out one's sample space, and is a fairly obvious example of how conditional probabilities are not symmetrical. Now for an example that is not so obvious. In forensic science, the most respected test that we have is DNA testing. Now, it should go without saying that the probability of getting a DNA match, given that we have the actual offender, is very, very high. If the person we're testing is the guilty party, their DNA will probably match. So far, so good. But what we want is the probability that we have the offender, given we have a DNA match. And since people share some parts of their DNA, and DNA can travel to places in multiple ways, here, whether we have the actual offender, given we have a DNA match, is going to depend on a few things. One of the most important things is our false positive rate, which should become obvious in this example. So this is an example from this super fancy expensive textbook called Weight of Evidence for Forensic DNA Profiles. It presents us with the island problem. So we have an island of 101 people, and there's a rare latent trait, and it shows up in about 1 in 100 individuals in this population. A crime occurs on the island, and everybody is suspect. This is Murder on the Orient Express style. Everybody's suspicious. But we know that the offender has a rare trait. So the person who committed the crime has this rare 1 in 100 trait. And we find an islander with that trait. What is the probability, given only the trait evidence, because remember, everyone's suspect, what's the probability, given only the trait evidence, that the suspect is in fact the offender? Now, some of you may be ahead of me because there are a few shortcuts to solving this one, but let's break it down into probability space, or break it out into probability space. There's 101 islanders. We know this. There's one guilty islander, and there's 100 innocent islanders. Well, so much for the whole Orient Express thing. Let's say that we're guaranteed a match if we test the guilty party. In other words, our test is good enough that we don't have to worry that it's going to miss, it's going to have a false negative. But since the trait occurs in 1 in 100 individuals, we have a false positive discovery rate here of 1 out of 100. So of the 100 innocent islanders, if we tested them all, we would expect to match 1 falsely. And since everyone's a suspect and we have no way of knowing whether the match that we've observed is this 1% likely false match, we end up with the fact that the test is bound to match the guilty party and 1 innocent party. So the denominator for our simplest equation of probability is going to be 2, and we have 1 match. That's the correct match. So the probability that we have that correct match is 1 over 2, or 50%. In other words, the chance of getting the trait evidence if the suspect was innocent is small, but the chance of the suspect being innocent, given we found the trait evidence, is still 50-50. The tendency to get confused by this is called the fallacy of the transposed conditional. So we had a probability of a match given that the suspect is innocent, and that is quite low. That was only 1 in 100. But the actual value we care about is the probability that the suspect is guilty or innocent given that we have a match. And that more important question for the trying of fact is what we call evens, 0.5. Put another way, saying this result would be very unlikely if the suspect was innocent does not mean that the suspect is likely guilty. Attempting to transpose the conditional in this way has a special name called the prosecutor's fallacy. So you emphasize the former, which is kind of irrelevant, in order to argue for guilt. The difficulty people tend to have in accepting this particular example of conditional probabilities not being symmetrical, or our tendency to transpose the conditional, is why we started with 2 examples that are easier. Don't just take my word for it with this example. Work on it until you understand it. Identifying fallaciously transposed conditionals can be a huge benefit to your understanding of things. For example, if someone is a mass shooter, they are likely mentally ill, a gun owner, and male. This does not mean that being any of these things, nor even all of these things, makes one likely to be a mass shooter. These things could, but the first conditional does not actually imply that they do, despite what our brain wants to do with it. Here's another version of a 4-cell table. In this case, we're looking at Toronto Public Health's mulling over of the decision of whether or not to release HIV protection pills. So these are pills that would reduce your risk of contracting HIV by 75%. Well, as long as the pill is safe, why wouldn't we just automatically give these pills to people? The concern of Toronto Public Health was, what if people go from being regular faithful condom users to using condoms less frequently? Because we know about your risk of transmission if you're using condoms versus your risk of transmission if you are inconsistently using condoms. The risk estimates are very approximate, but one is far more likely to transmit HIV if they are an inconsistent condom user versus a consistent condom user. One thing we could do is we could compute the 75% reduction and see what the risk for individuals is if they take the drug. So if you're taking the drug and you're using condoms, the 75% reduction of your original risk ends up being a 0.5% chance of HIV transmission. If you are an inconsistent condom user, your risk goes from 15% to 3.75% on the pill. So what Toronto Public Health was concerned about is migration from the 2% cell to the 3.75% cell. What if people who use condoms regularly migrate to the inconsistent use category as a function of having taken the pill? We know that if everyone who uses condoms regularly changes to inconsistent use after being on the drug, we can expect nearly a doubling of HIV transmission in those who migrated cells, from 2% to 3.5%. Such a complete cell migration, or behavioral change, would likely not actually happen, but it is a contingency that the Toronto Public Health would have to be responsible for if it happened. Without knowing the base rate of how many use condoms regularly and how many do not, we can't say whether, in a situation of 100% cell migration, HIV transmission would be overall going up or down. If nearly everyone was using condoms regularly, then the introduction of this HIV protection pill, if it made all of them do so inconsistently, then, in this hypothetical scenario, Toronto Public Health's intervention would increase HIV infection. This is why Toronto Public Health was concerned. But of course the pill was released. So, that was the 4-cell approach to mapping out reality, and at the end there we came across the importance of base rates. How many cases are represented by or expectable in each cell? That could have helped Toronto Public Health make a decision. The usual example to show the importance of base rates, or to introduce Bayesian statistics and its use of the base rate more generally, involves a positive breast cancer screening result, which we then translate into one's actual probability of having breast cancer given the positive test result, which, spoiler alert, is actually contingent upon how rare breast cancer is. We can do this roughly with the numbers available for HIV, though. So the base rate is how often something occurs in the long run. If you are a randomly selected Canadian, your base rate risk of HIV infection is roughly 0.007%. Roughly. The sensitivity for an HIV screening test is 99.99%. In other words, if you have it, the test will find it 99.99% of the time. So your chance of a false negative, or it being missed by the test, is 1 in 10,000. The specificity of a screening test, 99.98%. So if you do not have HIV, the test will say you do not have it 99.98% of the time. So the test works in both directions. Your chance of a false positive is 1 in 5,000. So here's another fourfold table. It contains all of reality. You either have HIV or you don't, and the test either says you have HIV or it doesn't. It's an amazing test, but it's looking for something that is quite rare. Given that a random Canadian's base rate risk of diagnosed HIV infection is roughly 0.007%, what is the chance that you have HIV given that you have tested positive? Here's how you would do the math to figure that out. You multiply sensitivity by base rate, and you divide it by sensitivity times base rate plus the false positive risk times 1 minus the base rate, which looks like this, which yields 25.9%. Even though it is an amazing test with amazing sensitivity and amazing specificity, the thing that it's looking for is so rare that even when it has said it has found it, it probably hasn't. So what would we do or decide in that case? Normally, we would then take a different type of test, designed less for sensitivity and more for specificity. But let's say we take the same type of test again. What we could do is we could use 25.9% as our new base rate. So we're upgrading our base rate from 0.007% to 25.9%. If our second test is positive again, well then we punch in the new base rate, and then we figure out that we can be 99.9% confident that HIV is present. Okay, so it took 2 tests showing a positive result to get us to 99.9% confident. What if this second test came back negative? How would we figure out how confident we can be in this negative result? We would have to swap out sensitivity for specificity and take 1 minus the disease base rate as our non-disease base rate in order to compute the following. Specificity times base rate divided by specificity times base rate plus false negative risk times 1 minus base rate, which looks like this and yields 99.996% confidence that HIV is not present. So we can see that even though we have an amazing test, if we change the base rates, the accuracy of the test changes. The base rate or the prevalence of something is an important part of interpreting any given test result. Despite this, some of the people we pay the most to keep society going tend to make rather egregious base rate errors. The general rule regarding statistical literacy is that 80% of whatever group you are testing will misapply statistical concepts, and this includes statisticians and instructors of statistics courses, who, for example, tend to misapply null hypothesis testing concepts. It includes medical doctors who tend not to understand or apply base rates with respect to tests, and to the judge who stated the test is of high quality. Doing the test again is not a fruitful use of the court's time. This is a quote from a case where the judge could have ordered a second test to rule out a false positive, which is what we did 2 slides ago with our HIV example. But the judge didn't order a second test, and he based it on the fact that the test has high sensitivity and specificity, just like the HIV test. Being high in these things is good, but it does not make the test free of error. If anything, it's an endorsement for using the test again, running that second test. The man on trial who was denied a second test spent a decade in prison before somebody finally reran the test, and the first result was, in fact, a false positive. He was set free, but he could have had a decade of his life not stolen away if the judge had been a bit more literate in how error base rates work. Note that the judge had transposed the conditional and conflated the low chance of error given guilt with a high chance of guilt given the result. In a case that made a different version of the same error, Judge Hellman concluded that an initial test had been so corrupted or impure that running it again with a similarly impure sample, the original sample, would not improve the determination of the test. It's the same error, not thinking that rerunning the test will add information. But in this case, the justification was that the test was poor. That's probably enough for today. Stay tuned.